Okay, so we resume our discussion of combinations with some problems. So this is the first one. What it asks us to form a committee of 3 people from a set of 2 men and 3 women. It asks in how many ways can this be done, and then there is a second part to the question. So let us proceed to the solution. You see, there are how many men available? 2 men and 3 women. So now, the committee that has 3 people, it can either have 3 women, it can either have 3 women, or it can have 2 women and 1 man, or it can have 1 woman and 2 men. Now, there are 3 women available. So, from them, we can choose 3 women in only one way, or if you prefer to use the notation, actually they can be chosen in 3C3 ways, right? And that turns out to be equal to 1. Why? Because if you see 3 factorial divided by 3 minus 3 factorial times 3 factorial. So these two cancel out and this becomes 0 factorial, and 0 factorial is 1. So this is equal to 1. So there is only one way 3 women can be chosen from 3 women, which is also obvious. I mean, we do not have to take the help of this formula. But in more complicated situations, this formula will save you. Now, the number of ways 2 women and 1 man can be chosen from this set of men and women. 2 women have to be chosen from 3 women, and that can be done in 3C2 ways. Okay, but corresponding to each such choice, 3C2 ways means it will turn out to be equal to 3. Say 3 women are W1, W2 and W3. And either you can choose W1 and W2, or W2 and W3, or W1 and W3. So there are 3 possibilities. But you don't have to think about that in this way. This symbol takes care of that and the formula that it represents. Okay. So that is the number of ways we can choose 2 women out of 3 women. But 1 man also has to be chosen from out of 2 men. So that can be done in 2C1 ways. And they are related because they are making the group together. Right? For example, why did I rub it off? If I have these 3 women and if I have these 2 men, then I can make the group like this: W1, W2, M1. But corresponding to this choice itself, I also have this another combination, M2. So that's why they have to be multiplied. Here also we are using the counting principle. So the number of ways of choosing 2 women and 1 man is this number. So this turns out to be equal to 3C2. If you use the formulas and you work through these calculations, after some time you will become accustomed to these values. You will know that 3C2 is actually nothing but 3. Similarly, 2C1 is 2. So this turns out to be equal to 6. Next, this one, one woman out of three women can be chosen in three ways. You choose any one of the three women, or symbolically in 3C1 ways. Now for corresponding to each such choice, two men have to be chosen from two men, which can be done in only one way or 2C2 ways. 3 times 1 equal to 3. So in total, the number of ways we can make a committee of three people from two men and three women is, you have to add this up. 1 plus 6 plus 3, which is equal to 10. So there are 10 committees that can be formed. If you want, you can actually do an exercise like this, where you take woman 1, woman 2, woman 3, man 1 and man 2, and you try to actually find these committees, and you will see that you get 10 committees. Now what the second part asks, how many committees consist of one man and two women? We have already found that out, right? As a part of this calculation, one man and two women. So this is nothing but 6. So the second answer is 6. Out of these 10 committees, in 6 of them, there will be exactly one man and two women. Okay? Now that one man can be any one of these two men. Right? Now we move on to our next question. Okay, this one has some parts or subdivisions. In how many ways can we choose 4 playing cards out of 52? In a pack of playing cards, there are 52 cards, as we already know. So out of them, in how many ways can we choose 4 playing cards? In how many choices A, will the 4 cards belong to the same suit? Will the 4 cards belong to the same suit? Belong to the same suit. B, will the 4 cards belong to different suits? C, let me write C here. Part C asks, shall we have 2 red and 2 black cards? And part D, will the 4 cards be of the same color? Be of the same color. Okay, so it has some parts, this question. So we start answering them one by one. The first one is easy. See, this is where our formula will come into play, because now the available choices are so many, 52, that we cannot hope to just envision 52 cards and then see how we take 4 out of them. That is next to impossible. I mean, for a computer it may be possible, but for us, although not impossible, but excessively time consuming. So instead, we just apply the formula directly. We have 52 distinct objects. From them we are choosing 4, any 4, and that can be done in 52C4 ways. Now this is just a symbol, but we know how to find the value of this symbol. This is 52 factorial divided by 52 minus 4 factorial times 4 factorial. And this turns out to be, well, it will be a huge number, or will it be? Okay, let me see. (48 factorial times 4 factorial. Can I simplify this? Times 51 times 50. Okay, let us not proceed any further with this calculation. This is enough. If you want, you can find the actual value, but this is what it is. Now, in this many ways, we can choose 4 cards from a pack of 52 cards without any further restriction given. But now the subdivisions start. Part A asks, among these combinations or among these choices, in how many of them will the 4 cards belong to the same suit? There are 4 suits, okay, clubs, spades, heart and diamond. So they have to belong to the same suit. Now, see, this can happen in several ways. It may happen that the cards that we have chosen are all diamonds, okay, say ace of diamonds, king of diamonds, queen of diamonds, jack of diamonds. It can be like that, or it can be a diamond of some, I mean, say 8 of diamonds, 7 of diamonds, 6 of diamonds, 5 of diamonds. So there are possibilities in that suit itself for choosing 4 of them, 4 of the cards. Okay, so in this case, what we are doing, we cannot choose from all the 52. We have to restrict our choices to the suits themselves. So if our 4 cards turn out to all be diamonds, then how many diamonds are there? 13. Each suit has 13 cards, right? So 13C4. In this many ways, I can choose the 4 cards so that all of them are diamonds. But that is not the only possibility. All of them can be spades also. All of them can be club also. Or all of them can be, what is the other one? Heart. So I will have these things, okay, corresponding to each suit. These are the ways of choosing 4 cards so that they belong to the same suit. Now, since the choices have already been made here, you see, this is the thing. 4 cards have already been chosen. So this is one case. Again, if this belongs to, say, hearts, this belongs to spades, right? Belongs to diamonds, and this one is clubs. Then this has already been chosen. The 4 cards have already been chosen. So this is one case. Here also the 4 cards have already been chosen, so this is another case. So these separate cases, when you find the number of them, you have to take their total by adding them. Okay, here we are not applying the principle of counting by multiplying them. In the other one we multiply, because there for example, you are forming a committee of 3 people, right? 3 people. So in that combination itself, there are men and there are women. So the choice of men, say, is affecting the choice of women. To form the total committee. So here, after choosing, say, there is the number of combinations where we have only 1 man and 2 women. So there were 2 men. So out of 2 men, 1 man can be chosen in 2C1 ways. Out of 3 women, 2 can be chosen in 3C2 ways. But neither this nor this completes the committee. Okay, together they complete the committee. So that's why they have to be multiplied. That is the principle of counting. Because corresponding to each choice here, there is a choice here. Here the situation is different. Here we have already made the choice of 4 cards. Then again here we have made the choice of 4 cards separately. Corresponding to these, none of these choices is affecting these choices or any of the other choices. So here we add them, or which turns out to be 4 times 13C4. So in this many combinations, you will have 4 cards of the same suit, and this number is going to be smaller than this number naturally, because in so many of the combinations here, the 4 cards may be from different suits, and that is the next one. See, will the 4 cards belong to different suits? Okay, this is not exactly the thing that I was thinking of. Here 4 cards belong to the same suit. 4 cards belonging to different suits is something, and 4 cards not belonging to same suit is something else. Okay, had it been asked, will the 4 cards not belong to the same suit, we would have subtracted this number from this one to get that answer. But here we have been specifically asked how many of these combinations will give us cards coming from different suits. Okay, this is an entirely different situation where 2 or more cards are not allowed to be from the same suit. The 4 of them should come from different suits. So this is not what I was thinking. But this also has a way of solving. So what I am trying to say here is that the answer to part B is not this minus this. Okay, it's not a situation like the ones we have come across in some other problems involving permutations. It's a different thing. Now you see, the 4 cards have to come from different suits. Okay, so our combination still consists of all the combinations we are considering here in this problem. Each one of them consists of 4 cards. Okay, so that is fixed. But the way we are choosing them, that is changing in the parts. So now say I want to choose this one from the diamonds, say. Okay, and this one from, okay, by the way, do not think that this is permutations. Since I have written like this, it does not mean I am trying to find the arrangements. We are not concerned about arrangements anymore. We just are concerned about the choices or the groups that they form, the chosen elements or objects. So a diamond can be chosen. 1 diamond should be there, right? 1 diamond, 1 spades, 1 club, and 1 heart should be there. So A diamond can be, how many diamonds are there? 13 diamonds, right? One diamond can be chosen from 13 diamonds in 13C1 ways. In the same way, one spades can be chosen from 13 in this many ways. Similarly for, diamond I have already taken, club and heart. The symbols don't matter, the numbers matter. 13C1. And you see, these choices together make our one combination. So here we have to apply the counting principle. So that's why we are multiplying. Do you see the difference between this and this? Here the 4 choices have already been made, but here they together make the 4 choices. So that's why we are multiplying. So in this case the answer is 13C1 to the power 4. And since 13C1 is 13, you can see that it is 13. So this is 13 to the power 4. Okay, 169 times 169. Part C. What does part C ask? In how many of these combinations shall we have 2 red and 2 black cards? Okay, so 2 red, how many red cards are there? This is red. Diamond is, any diamond is red and any heart is red. So in total there are 13 plus 13, 26 red cards. Now 2 red cards have to be there. So 26C2 and 2 black cards. So likewise there are 26 black cards. So 26C2 ways of choosing black cards. Together they make the combination, so we multiply them. So this is the number of combinations or groups in which we will have exactly 2 red cards and 2 black cards. Finally, part D. Will the 4 cards be of the same color? Okay, now there are 2 colors, again red and black. So will the 4 cards be of the same color? You see, if the 4 cards are red, then that can be chosen in 26C4 ways. Okay, why? Because there are 26 red cards. So from among them we can choose 4 in 26C4 ways. Similarly, the black cards can be chosen in this many ways. Since the choice has already been made here, we have chosen 4 cards. So this here also we have chosen 4 cards. So these are separate cases. That's why here we don't multiply, here we add. 2 times 26C4. You can calculate these numbers using calculators, or if you want you can do hand multiplication also, but that is not the thing. I mean, that is not something to be considered here. The technique is important. So you see that although in mathematics the people who don't really know about it that well, all they see is calculations and some formulas, but the actual arithmetic of finding these answers, that is an entirely different thing. Okay, some people think that some calculating savants, people who can do mental calculations at an amazing speed, although that is a very, what to say, that is a very nice talent to have, but they are not mathematicians, and they can find some quite deep results in number theory, but calculations are not what mathematics is all about. Okay, rather calculations are just a small fraction of it. The symbols are not, you see so many symbols in some board of a mathematician. I'm not a mathematician, I'm just a student like you, okay, who is trying to understand the things clearly. In a board belonging to some office of a mathematician, you will see many symbols. So when we look at those symbols, we think, yeah, that this is mathematics. That is not mathematics. That is just a language of expressing the ideas. There are ideas behind those symbols. Okay, so that is mathematics, and that is interesting. The symbols, well, okay, they look messy and they look somewhat intimidating to the ones who don't understand their meaning. But that's not what it is. The symbols can be written in some other way also. Okay, some equation, instead of writing an equation like this, you can say change the coordinate system or make some sort of transformation. The equation will change, but the thing that the equation is representing, or the two equations representing, that remains the same, and that is the actual important thing. Okay, so now we move on to the next one. The next question asks, how many chords can be drawn using 21 points lying on a circle? So if you recall from your elementary school level geometry, Euclidean geometry, if you have a circle, then corresponding to a circle there are three different types of straight lines, right? A straight line can lie entirely on the outside of the circle, or it may touch the circle at only one point, or it may intersect the circle at 2 points, right? These are the three distinct situations we can have. Now, in this situation, this line segment that you have in between the points of intersection, this is called a chord. A chord that is of maximum length passes through the center, and you know it's called a diameter. There are infinitely many diameters. Like that, there are infinitely many chords. Now, what this question asks is that there are 21 points. In some way, they are lying on a circle arbitrarily. So there may be many different chords between them. There will be many. How many? We have to find that. So you can see that for forming a chord, we need 2 points, right? So to know how many chords are there, we just have to see in how many ways we can choose 2 points from these 21 points. And the answer is immediate, isn't it? 21C2. So this many chords are possible. If you want, you can just, okay, for this one, let us actually calculate the number. 21 divided by 21 minus 2 factorial divided by 2 factorial. So this is 19 factorial times 2 factorial. So, and 21 can be written as 21 times 20 times 19 factorial. So these two cancel out, and we divide 21 times 20 by 2. So this becomes, if you can divide 20 by 2, you get 10. 10 times 21 is 210. So you get 210 chords. Okay, that can be drawn using this 21 points line on the circle. So you see that even 21 points give you so many chords. Then the next one, so these are just some practice problems to make ourselves more comfortable with the concept of combinations. In how many ways can be, again, a group problem, in how many ways can we form a group of three boys and three girls from five boys and four girls. Okay, so now we are given the number of boys and the number of girls. In the group there must be exactly 3 boys and exactly 3 girls. So in total there should be 6 people in the group. Now how many boys are available? 5 boys. So from 5 boys we can choose 3 boys in 5C 3 ways, and from 4 girls we can choose 3 girls in 4C 3 ways. And you see the addition and multiplication, as I have been saying all this time, since the group has to have 6 people, so neither this choice nor this choice alone makes it complete. You need both of them, and that's why they are affecting each other. So that's why we put multiplication. So this is the answer. Okay, so let me take the next question. Let me write it here itself. We have 6 red, 5 white and 5 blue balls. We have 6 red, 5 white and 5 blue balls. In how many ways can we choose in how many ways can we choose how many? 3 balls of the same color. 3 balls of the same color. For each color. Okay, so 6 red balls, 5 white balls and 5 blue balls are available. In how many ways can we choose 3 balls of the same color? Right. So the 3 balls have to be of the same color. Now here the number of objects we are choosing is 3. Okay, just like here the number of objects we are choosing were 6, but here it is 3. So the 3 ball can either be red or white or blue. So the answer clearly is 6C3 plus 5C3. This is the number of ways of choosing red balls. This is the number of ways of choosing white balls. And again, the number of ways of choosing blue balls is 5C3. Now, in this question, I have a confusion. The confusion is whether the red balls are distinguishable from one another or not. If you see, for example, you have some billiard balls, say red balls, some 6 red billiard balls. If you cannot really distinguish between them, then this will not be the number of combinations. The number of combinations will be 1 plus 1 plus 1, because you see, if you have these